In this paper, we investigated the recently proposed shuffler-based differential privacy, and we improved its utility and security. Differential privacy is used in the 2020 US Census for publishing demographic information about every individual in the nation. Census possesses the true data and wants to share it, but it is also forbidden that such data cannot be directly shared because it contains sensitive information about individuals. So in this case, Census uses differential privacy, which allows them to inject a precisely calibrated amount of noise to carefully control the privacy risk of any data publication. And this is listed as one of the 10 breakthroughs in 2020. The example from the census is in the government setting where the central server is being trusted by all the users for data collection. But moving to the industrial setting, companies such as Google and Apple are not necessarily trusted, so they are using the technique called the local differential privacy. More specifically, in local differential privacy, noise is added by each device locally, so there is a virtual protection between the device and the server. After users send their data, the server can learn things like frequent emojis and then, for example, make predictions when we type things using the keyboard. The technique is pretty cool and very promising in that users now don't need to send their data directly to the server and will trust the process and consequently be more willing to share their data. However, one major challenge of local differential privacy is that the amount of noise is quite high, so the use cases of local differential privacy is quite limited. This figure shows the comparison between the traditional or central differential privacy and the local differential privacy. In the central differential privacy, the server needs to be trusted and users need to send their data directly to the server. In the local differential privacy, users, on the other hand, don't need to trust the server, but the overall noise in the local setting is much higher. And more recently, there is another model between the central differential privacy and local differential privacy, which utilizes the two parties. I will describe how this works later, but the desired goal of this model is to achieve a middle ground between differential privacy and local differential privacy. Namely, users only need to trust that the two parties won't collude. For example, here, the original server is Apple and the newly introduced server or the shuffler is from Microsoft. So the companies will cooperate and collaborate, but they will not collude with each other. On the other hand, this model had the advantage that it introduces much less noise than that in the local differential privacy model. So how does this model works? In this setting, the users still use local differential privacy to add some noise, and the users will encrypt the result with two layers of encryption. The shuffler has the decryption key of the outer layer of the encryption and can get rid of the outer layer. However, there is another encryption layer, so the shuffler still sees encrypted format of the local differential privacy data. The shuffler then shuffles the data and sends it to the server. And finally, the server will decrypt the result and add some and do some local differential privacy estimation. The model is very exciting, and researchers studied it extensively. A lot of good results about the utility are obtained. But the message we want to convey in this talk is that the security aspect of this model is less studied, and we want to have a more secure model in this case. So in this paper, we did a thorough analysis of the security aspect of the model. We found that the newly introduced party can be malicious and will do bad things to the model. In particular, we found two kinds of attacks, collusion and manipulation. Collusion means that if the party collude with the server, then uh, if the third party or the shuffler collude with the server, then the model is downgrading to be the same as the local differential privacy model. And on the other hand, manipulation is the attack where the shuffler can poison or just change the original result in an arbitrary way to benefit the shuffler itself. We then came up with some defense ideas. First, to reduce the risk of collusion, it is pretty natural to introduce more shufflers, and the likelihood of the server colluding with all the shufflers is smaller. So the shufflers can also add dummy reports to further protect the users. On the other hand, to defend against manipulation attack, we propose to use a protocol called oblivious shuffle. It works in multiple rounds, and in each round, only half of the shufflers will know the order, and the other shufflers will be oblivious to the order. It utilizes additive homomorphic encryption, which sort of split a secret into multiple random pieces, but they will sum up to the original secret. So to design a protocol is typically not easy. To design a secure protocol is typically not easy, and there will be different issues. And in many cases, if we patch one issue, another issue will appear. So in this case, we found that if we introduce multiple shufflers, they themselves can collude. So to prevent the shufflers from colluding among themselves, we introduce homomorphic encryption to the oblivious shuffle protocol. And homomorphic encryption ensures that multiplying two ciphertexts give a ciphertext of the addition of the two plaintext. So this slide shows an example of how our final protocol works. So we assume in this example, there are two users and their local differential privacy data are A and B respectively. And they share their value to the three shufflers. One of the shufflers will receive shares encrypted by homomorphic encryption, and this ensures that even all the shufflers come together, they still don't know the original local differential privacy data. The shufflers can also add dummy local differential privacy data denoted by the light blue color. Note that the shufflers only draw shares of C and D, so as long as one shuffler is honest, C and D are random and can protect the privacy of A and B. Now, one shuffler further splits its shares and send the shares to the rest of the shufflers. The two shufflers receive the share, add them up to the original shares, and use the same order to shuffle their shares. Then the two shufflers further split their shares and send some share back to the first shuffler. And this process will continue for multiple rounds, each initiated by a different shuffler. And finally, the shares are sent back to the original server who obtains the shuffled version of the original local differential privacy data. More details are in the paper, and we also had a utility analysis part in the paper. We encourage interested audience to read our paper, and I'm happy to take questions. Thank you.